Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the cosmic distance debate, or more specifically, how we know the distances to the far galaxies. We've been looking at distances to stars using parallax, and now we're going to be looking at the distances to extraordinarily distant objects, the systems of stars like the Milky Way, but much further. And this debate was one of the most important things that happened in the early 20th century, and we're going to see some of its history, and we're going to see how it resolved. But the real important thing is, as we look at these stars, we have no idea what their distances are a priori. We just see them as points of light in the sky. And whether or not they were distant objects has been the subject of wonder for thousands of years. And only in the early part of the 20th century did we finally get a glimpse at how far they are. So the distance problem is incredible because getting distances will always be the biggest technical problem in astronomy, and frankly, the most important thing to relate astronomy to astrophysics. Because if you don't have distances, you can't know the luminosity, size, mass, or the distribution space of objects. And without this, you can't understand their lifespans, how they were born, how they live, how they die, what they do, how they evolve, or anything. So distance is the key thing in astronomy, and it's also one of the most difficult things. All right, let's see how difficult. Very early on in previous lectures, we talked about the astronomical unit, and the astronomical unit is incredibly important because it forms the baseline for trigonometric parallax. Copernicus used geometry of the orbits of the planets in order to determine the relative distances between the planets, and that was something that could be done. But it took until radar was invented to really get very solid planetary distances using the speed of light and being able to reflect radar off of objects, such as Venus when it's at quadrature from the sun, so it has a phase of a quarter phase as we see it, and that allows us to measure the distance to Venus relative to the sun and give us the astronomical unit by simple ninth grade geometry. And therefore we can use trigonometric parallax, which is the measurement of distant stars. But trigonometric parallax, which is the apparent motion of a foreground star with respect to much more distant stars, as a result of the Earth's orbit around the Sun and the apparent change of that location, has a distance limit. On the ground, the best you're going to get is 1/100th of an arcsecond, and that's going to be using adaptive optics. But the Hipparcos satellite in 1998 was incredibly good because it got out to about 1,000 parsecs. And that is an important distance measurement because that got the accurate distances to about 100,000 or so stars, roughly in that ballpark. The Gaia satellite, though, greatly improved upon Hipparcos in 2016 with its first data release that got to 1% of 1% of an arcsecond, which goes out to about 10,000 parsecs and has at least 1 billion stars inside of that area. So the Gaia satellite has radically improved distances using parallax, which means distances are much better known to many more objects, which allows the physics to be better known. So we're going to define a new kind of distance that is secondary to parallax distance, because parallax is the only geometric way of knowing things. It's the only direct measurement of distance, and that's why Gaia was such an important mission. But the luminosity distance is just as important. How you do it is you measure the brightness of some object in some filter, say, and then you have some way of knowing or estimating, guessing, positing, or VGing out of the air the luminosity of the object, and then you solve for its luminosity distance by applying the inverse square law of the brightness. And that's what we see here. D sub L is the luminosity distance equals the known luminosity of an object divided by the brightness that you observe it to be times that 4 pi, and you take the square root. So you have to know the luminosity first. So it helps to actually get the luminosity from, say, a parallax of an object. But that tells you something you need to know, which is the nature of a standard candle. A standard candle is something where you already know the luminosity a priori. And if you do know the luminosity before you take its distance measurement or its brightness measurement, then you have what's called a standard candle. And you can calibrate standard candles in many ways, but I just alluded to it before. Take the luminosities of nearby objects where you can get the parallax, and then you find similar objects using some sort of distance-independent property that they share. Maybe the spectrum, maybe some variability, maybe something, who knows, maybe it's got a smiley face. And you assume that the distant objects have the same luminosity as the nearby objects for which you have the good distances. That's interesting because the step 2 to step 3 assumes that the laws of physics are the same everywhere. And that's what we're always going to assume, that the laws of physics that are nearby us that we would measure in the laboratory apply to distant stars. So we can use the ideas of physics in order to reach out into the cosmos, because we really can't in any other way. So once we get that calibration set of standard candles, then you can measure them for things that are too far for parallaxes. But the trick is this distance-independent property. And every distance-independent property relies on physics, and so we must assume that the laws of physics are the same there as they are here. And in this little diagram, it shows, well, if you have a candle that's of known brightness, you put it farther away, it looks dimmer. And likewise, another distance-independent property is the physical size of something. So the farther away it is, the smaller it appears. But there's very, very, very few standard yardsticks. But there are a few very critical standard candles. And so one of the more important ones is the spectroscopic parallax, because you can easily get the temperature of a star by either looking at its spectral type or its B minus V color or some other color variation. And if you have a well-calibrated HR diagram, then you simply have to say, oh, I know it's this kind of star because the luminosity class tells me it is a bright giant, so therefore it's an A81 type star, not an A8 main sequence star. It's an A8 bright giant, not a dwarf. Dwarf would be dim, giant would be bright. And so you can then say, I've got the spectral type and luminosity class, and that's for stars, which are incredibly bright objects that you can see from a distance. Likewise, if you calibrate the HR diagram, then you could say using a known HR diagram, such as the Hyades, the Hyades then becomes the basis for all your other HR diagrams. And so the only reason the Pleiades looks different, its main sequence looks dimmer than the Hyades, meaning a V magnitude that is larger, but the same colors for the same stars, is because the Pleiades is farther away, and so the distant, they just are simply fainter and therefore have larger V magnitudes for exactly the same kind of star. So you calibrate all of these things, get distances to Pleiades, get distances to Hyades, and many other things, and the Hyades itself forms the basis for all of this calibration. So it is the most critical of all of the nearby clusters. And we can therefore build the cosmic distance ladder out of extraordinarily nearby objects. So what we have is a power of 10 in distance. Each time we go up 10, the number across the bottom means something's about roughly 10 times more distant than the other in terms of parsecs. And parallaxes get us out to, say, now much further than we had thought. But originally, the parallaxes got us out with Hipparcos only about 100 parsecs or so. But that's how far we can see now with the parallaxes, up to 10,000 parsecs. And we can use proper motions of stars in order to get us there. But then we can use parallaxes to get us to distant clusters with main sequence fitting. And that's where, or spectroscopic parallax work. But the next one we're going to talk about, the RR Lyrae and Cepheid variables, are incredibly critical because the study of the LMC, or the Large Magellanic Cloud, and then getting the distance to M31 is the subject of our next conversation, which takes us out to a megaparsec, or 10 to the 6th parsecs. So there were no ways to get parallax or proper motion, or even a group of stars that we would call a cluster in M31. So exactly how far is the Andromeda galaxy, M31? You have to use RR Lyraes and Cepheids to get you there. So let's see how that was done historically. And the details are coming in, because off to the left on this thing with this picture from CTIO, we see the large and small Magellanic Clouds in the center of the Milky Way to the right, but the LMC is on the bottom and the SMC is on the top. And those clouds are actually galaxies, and they're orbiting the Milky Way, and that's what we know now, but we didn't know their distances. And what were those objects? And that was the study of the subject that we're about to talk about. So let's take it back in time. The concept of distance and how big the universe is took a big step forward in 1610. So after thousands of years of looking at the stars and simply knowing that they're far, but thinking they were pasted on a celestial sphere, the Starry Messenger was published by Galilei in 1610, and what he showed was that the galaxy itself is a lot of stars. So he took his tiny telescope and looked at the Milky Way, and these drawings that he did of the stars showed many faint stars that he couldn't see by eye. And so if we look at the Milky Way on an extraordinarily dark night where there's no light pollution, which they didn't have in 1610, I mean, it was actually dark sky, unlike today where you can barely count 50 stars. Back in 1610, a night sky in the city was actually dark. And so you could see many, many, many stars. But through the telescope, you could see more. So therefore, he knew that the galaxy, meaning the Milky Way, was just many, many stars that were faint, that just blended together, that could be resolved with a telescope. And that was the first inkling that the Milky Way was much, much, much bigger. In 1750, a theologian named Thomas Wright created a model of the Milky Way based on theological ideas, and his goal was really a wacky concept, but his goals, basically he said, well, the sun is in some grand shell around the center of everything, and so if we looked along the edges of the shell, we'd see more stars, which is similar to what we see in the sky. We see a shell or a ring in the sky. So if we were in the middle of that ring, we would see stars in that ring around us, and it would taper off. But looking above and below that shell, we would see fewer stars. And so his model has, kind of explains the appearance of the sky, but this was his real model. So he was looking at the concept of the theology behind the starry work, and we were in one of many stars inside this grand shell. His conceptualization was that somewhere in the center of some grand shell, which we could not perceive, was God, and God looked out at the rest of the stars around him in the firmament, and all of those stars held innumerable planets, and you can kind of see it alluding to it in this thing. And so his concept was theological, and if you go hunt around at Thomas Wright's work, you find some really trippy stuff. And it's always got these little stars with eyes in the center. It's very Illuminati. But anyway, that was 1750. Well, people like William and Caroline Herschel in 1785, they were a brother and sister pair, and William and Caroline Herschel were arguably one of the most important astronomers in history. They decided, after building a 4-foot diameter telescope together, where William ground the mirror while Caroline fed him bananas over the course of many days and kept him going so that he could keep his arms moving so that the glass could take the shape that they wanted. But what they did is eventually, after many, many years of trying to build this telescope, eventually they constructed the whole thing and started looking out into the sky and looked in many, many directions, about 683 directions, with their big scope. And they assumed that all stars had the same brightness. And if you really don't know anything better, you might as well assume that. And so therefore, if stars are at certain brightnesses and they're all the same brightness, then how far they are is simply their relative brightness. And so this is starting with the concept that we now know is not true, but in 1785 was a good guess, to say that all stars have the same brightness, and then assume that their distance is based on that. So they assumed that all stars were standard candles, which we know they are not, but still 1785. So they did pretty good. And so this gave them the first map of the universe, the first one ever made. And so the sun was off to the side. We can see the effect of the edge of the galaxy in that little dip where the nodules are with these two little arms, like an amoeba shape off to the left. And so we have this enormous, enormous shape that would be maybe called a grindstone, but the sun's not at the center. There seems to be many, many more stars to the left than there are to the right. And to them, this was the map of the universe. Now, there may very well have been things beyond this, but to them, this was it. These were the stars in the sky. So we seem to be one of many in this kind of patch. And then in 1755, which is prior to this, so we're going to bounce around a little bit in time, Immanuel Kant's a philosopher. In 1755, he looked at Thomas Wright's model of a disk and thought, this seems to be about right. And Immanuel Kant said, well, maybe the universe was a lens-shaped disk and was rotating about the center. And the sun was not really any special star in there, and all these other nebulae that were being discovered were rotating Milky Ways similar to our own. And what was being discovered was William Parsons, the third Earl of Rosse. And in 1845, about 100 years later, built a big telescope in Parsonstown, and he discovered these things called the spiral nebulae. Now, the spiral nebulae looked like disks, but they had some sort of spiral pattern. Some of them looked edge-ons, but with dark bands slicing through the middle, but he could not resolve any of them into stars. I mean, his telescope, while enormous, didn't have the resolution that we think of for high-resolution telescopes today. So this was a big deal, and the structure I don't believe stands today, but this enormous telescope could not be pointed very much to the left or right, but it could certainly be pointed up and down. And using this, he visually recorded the appearance of galaxies that he called spiral nebulae, or nebulous cloudy objects in the shape of spirals. All right, Kant's idea about a 1755 idea, Alexander Humboldt looked at Parsons' spiral nebulae and said, those are other Milky Ways. They're just made of stars. And so they're very, very, very far away. So he thought those disky sort of things have the same appearance as the Milky Way, but just viewed edge on and far away. So Alexander Humboldt said the Milky Way is an island universe of lots of stars, and there are many, many, many other galaxies out there, and we're just one of them. However, a very famous mathematician, Pierre-Simon Laplace, in 1796, prior to that, we're going to be bouncing around in time, of course, posited that the spiral nebulae that were being seen were actually swirling gas clouds that are in the process of forming planets and solar systems. So gas clouds should collapse under gravity, and as they collapse, they'll form disks if they have any rotation, and this is what Laplace posited. And the solar system is in a disk-like shape, and there's numerous examples of gaseous sort of phenomena, and these were seen in telescopes and in the Orion Nebula. And so people could actually say, well, if there's a disk-like shape, and so if there's spiral-like structures, then these must be spiral formations of new solar systems being found. Now, if they're new solar systems and they're nearby, maybe the rotation can be discovered. And Laplace's idea took more of the Herschel's idea to heart and said, the only things we see in the sky are nearby stars and nearby objects, and so the Milky Way is the universe. And so this is the nebular hypothesis for the spiral nebulae. Well, it was not really understood what the heck is which way to go, and until about 1906, Jacobus Kapteyn said, let's actually do something with this. And so he started saying, let's do photographic star counts in many different directions. And so he took Herschel's idea, but then he said, let's photograph stars and measure the apparent magnitude, spectral type, radial velocity, and proper motion of many stars in a bunch of different zones, over 200 zones. And this huge project had lots of different observatories, 40 different locations, and his process was enormous. It took almost 20 years to complete, approximately 16 years to actually do the whole thing. In 1922, he published his concept of the map of the cosmos, that the universe or the Milky Way or what have you, the galaxy itself, the sun was not at the center. There were lots of stars. Many of them were very far. The diameter of this disk-like structure was about 17 kiloparsecs, or 17,000 parsecs, or 40,000 light years, and about 12,000 light years thick. The thing is that his problem was that he did not understand what interstellar reddening was, and he vastly underestimated it. In fact, nobody really had a good handle on it at that time. But there were other things that were being discovered. And we're looking here at a Kepler Space Telescope view of the globular cluster Messier object number 4. And as you can see, some of the stars seem to be blinking on and off. And this is from Hartman and Stanek of Harvard Center for Astrophysics. And this is using the Kepler mission in its K2 mode, as it only has 2 reaction wheels to help keep it stable, so it can only focus on this area of the sky for a short period of time before it must move on. So one of the objects that Kepler in its K2 mode studied was this globular cluster, and we can see that there are particular kinds of variable stars called RR Lyrae. They literally get brighter and dimmer with time. So these RR Lyrae stars have a particular brightness profile and how they get brighter and dimmer. What's the pattern of brightness and dimness? And they're called RR Lyrae. So if we measure the brightness profile, how they get brighter and dimmer with time over RR Lyrae, they have this particular shark tooth pattern where they rise quickly in brightness and dim slowly. And then they rise quickly and dim slowly. And this is characteristic of the type of variability that you find with an RR Lyrae. So we attribute a distance-independent property to the variability. So there's a variability that seems to be characteristic of some class of objects, and we call them RR Lyrae stars. So maybe there's something that we can use with this. All right. In fact, if we look at RR Lyrae itself, this is the data from the American Association of Variable Star Observers. And this data is actually, you can derive it. You can just go to their website and say, please show me the data for this and download it. And this is in numerous filters. And this has been contributed by many, many, many amateur observers as well as professional observers who are showing the brightness variation in different wavelengths. And so that's what the different colors indicate, in different wavelength bands of light. So RR Lyrae stars are actually physically pulsating stars, and they're found in old clusters, such as even in the galactic bulge or in the halo, and they will be found in globular clusters. So these are old stars that are dying, and they physically are getting larger and smaller. And they have this particular pattern that we saw, that shark tooth pattern, and that particular pattern is a distance-independent property. And so maybe there is a relationship between that, and it so turns out that there is. RR Lyraes are roughly vary between like a few hours to maybe a day or so to get brighter and dimmer. And at their brightest point, they are as bright as about 100 times the luminosity of the sun. So all you have to do is find the variability of it and figure out that it is this kind of variable, and it has that particular pattern, and then see what the brightness is that you compare it and say, oh, all of these stars have roughly the same luminosities at the peak. And then, so it's an RR Lyrae type star, then there we go. So this is a period luminosity relationship for the period of variability for an RR Lyrae to the brightness that it gets at its maximum. And this is an important thing. So Harlow Shapley utilized this concept to study the distances to the globular clusters. So he was working with them, and he found that using RR Lyraes as a distance indicator, because you could figure out their luminosities, with their luminosity you could get the distance because you could measure the brightness, yada yada. And so he noticed that they were uniformly distributed above and below the Milky Way, concentrated towards the direction of Sagittarius, and they seemed to be physically, or at least dynamically oriented towards that as their center. And using that, he said, well, assume that the center of the globular cluster distribution is the center of the Milky Way. And when he made that position, he said, wow, that makes the sun approximately 18 kiloparsecs from the center of the Milky Way. It's really quite distant. But again, he had problems with interstellar reddening. So he overestimated the distance. But still, that gave us a good distance to the center of a distribution of the globular clusters. Now his results, and so if he takes the whole thing into account, it makes the Milky Way look to be about 300,000 light years across, or 100 kiloparsecs across. The sun's about 16 kiloparsecs, or 40,000 light years from the center, or 50,000 light years from the center. He didn't know the full extent of interstellar absorption, so he overestimated distance. I mean, everything that he said was bigger was too big and too far. So what is this interstellar reddening that we talk about? Well, we did talk about it previously when we talked about stars and exactly how they make up and interstellar gas. But we know that interstellar space is filled with this dust and gas, and we know that dust absorbs and scatters blue starlight. And so since it does that, it makes distant stars look red and faint. The stars become, or their appearance looks redder because the blue light's been scattered away, leaving the red light. So if you don't really know, if you can't take this well into account, then you're going to say, wow, that thing's really faint, but it's this kind of object, so it's really, really far. If, say, the light from RR Lyrae is going through a cloud, like you see in these two images below, then it's going to look fainter. And so you'll think it's farther because you're saying how bright it looks, and you're assuming there's a luminosity period relation, not a brightness period relation. That means that Shapley and Kapteyn thought that everything was much further than it was because they underestimated the effect of interstellar dust. And so only in 1930, well after this debate was settled, which we'll talk about, we discovered that interstellar dust absorption was extraordinarily significant. And so that is one of the more important elements of 20th century astronomy, is really measuring this stuff. All right, but let's take it back to the 20s. How big is the Milky Way? How distant are these spiral nebulae that the Earl of Rosse discovered, these spiral-shaped nebulae that he saw visually? And there were two competing concepts for what the Milky Way was. One of them was that the universe is the Milky Way, and so the spiral nebulae the island universe said that we are one of many islands throughout the entire universe, and our galaxy is just one of many. And so the cosmos is extraordinarily large, and we're just a tiny little thing inside it. That seemed a little difficult for astronomers that time, and most preferred the nebular hypothesis. And the nebular hypothesis said the spiral nebulae are simply gaseous clouds, and they knew about a lot of gaseous clouds and nebulae of such forth. They just happen to have a spiral shape. And if we have a spiral shape, and they might be forming planets. And so planets did exist around stars, and stars had to come from someplace. And Laplace was right that gas clouds should collapse under gravity and then rotate. And if they rotate, they're going to form a disk. If they form a disk, they might form a spiral. So the nebular hypothesis at that time was the most compelling. However, the island universe one was also compelling because of the physical characteristics of the spiral nebulae. So let's see how this worked. And so we have a number of people at Harvard who were working to classify stars, and Annie Jump Cannon and the rest of the group were busily working on the nature of stars and cataloging stars, and they were the computers at Harvard. And one of them was Henrietta Swan Leavitt. And Henrietta Leavitt was doing some work finding variable stars in the Magellanic Clouds. And by 1912, she found these brighter variables had these longer periods. So she was the one who first discovered the period luminosity relationship of Cepheid variables, a new type of variable star. But at the time, she had no way of actually getting the luminosity calibration, so she didn't do it. But let's call it the Leavitt relationship because that's what they really are. The Cepheids and RR Lyraes do have this brightness that varies regularly with a distinct pattern. And so delta Cepheids and RR Lyraes, she discovered the period was directly related to the brightness, and that was her discovery in 1908 and worked on through 1912. And this was what she was working on when she was studying the Magellanic Clouds to find their distance, because she found these variable stars inside the Magellanic Clouds while she was trying to find their distance. And again, delta Cepheids are similar to RR Lyraes because they're pulsating supergiant stars, not just giant stars, but they're supergiant stars, and they're found in young star clusters, so you might associate them with star-forming regions. And they're really, really, really bright objects, and they are luminosities between 1,000 and 10,000 times that of the sun, but their periods are much longer, between a day and up to like a month or two. And so she discovered that they have a particular profile and that differs from the RR Lyraes, and so you could calibrate the delta Cepheid luminosity period relationship. And they can be distinguished, in fact, individual ones, because of their brightness, can be distinguished out to almost 120 million light years using the Hubble Space Telescope. But the problem is that Cepheid variables are rare. And as rare things, there's very few Cepheids that are nearby, so it's very difficult to get their parallax. And there's also even two different kinds of Cepheids. There's the delta Cepheid and W Virginis stars. So they're both the same kind of thing, but they have slightly different period luminosity diagrams, so you have to be careful with which kind you found. So delta Cepheid, even still, because of their intrinsic luminosity at their maximum, they're incredibly important standard candles. And so we can see that here is some of the images for some of their variability. This is from the Ogle group, and we can see that Leavitt's relationship that she saw was actually in the Large Magellanic Cloud, or LMC, is that the time between the peaks, the longer the time between the peaks of the variation, the brighter they are at the peak. So this is the relationship that Henrietta Leavitt found, and that was used to try to get the distances to the Large Magellanic Cloud and thus further as well. We can do an example one where you say, given a well-calibrated Cepheid relationship, specifically the Leavitt relation, if you find one that has 10 days long for how it gets bright and dim, then we know it's about 5,000 times the luminosity of the sun. And that's incredibly important because now all you have to do is find the periodicity, make sure it's the same kind of character as a Cepheid, not an RR Lyrae, but a Cepheid variable, meaning their light curves, how they get brighter and dimmer with time, is different between RR Lyraes and Cepheids. You just read it off if you can find one that has a 10-day period. And if we go back to the original HR diagram about the lifespans of stars, we find that Cepheid variables are supergiant stars that tend to be much larger and young stars. Maybe they're O and A and OB and A stars that are in the time of leaving the main sequence or are dying. And so they are horizontal giant branch stars that are their variability comes as a result of physical oscillations of the star actually getting larger and smaller with time. And any star that's inside this instability strip shows some sort of variability, either Cepheid variability or RR Lyrae variability. And these are evolved stars off of the main sequence. Let's take a step back. Problem is that her boss, Pickering, kept her from following up on the relationship. However, in 1913, just a year later after Leavitt published her ideas, or at least tried to publish them, he calibrated the Cepheid her relationship and took some credit. And then said, well, these are Cepheid variables. Oh my goodness, let's do the necessary luminosity calibration. Did so. 1915, Shapley came in and refined the calibration for the globular clusters of RR Lyrae, which allowed him to start his work. So basically, Henrietta Leavitt gave this whole thing its start by discovering them and determining that there is a period luminosity relationship there. In 1920, about 5 years after Shapley did his work, the National Academy of Sciences had enough of this stuff, and they decided, let's figure out the size scale of the universe, let's bring everybody in a room, and we'll have a big fight. And it's called the Curtis-Shapley debate that happened in 1920. So Shapley from Harvard defended his model for the galaxy and the very conventional, based in a lot of well-understood physics, the nebular hypothesis, which said that the Milky Way is the collection of all stars in the universe, and outside of that is a great vast void. And the spiral nebulae are local to the cosmos. However, there was an upstart astronomer named Hipparcos at the Lick Observatory who defended Kapteyn's model that the universe was very, very large, and entertained the concept that the island universe hypothesis was the right one, meaning that the Milky Way was one of many. And so Shapley utilized physics and the postulate of the formation of planets and stars. And Hipparcos utilized the idea that the spiral galaxies or the spiral nebulae looked very similar in appearance to our Milky Way. Like things must be like objects. So the big battleground questions of their debate were, how big is the galaxy? What was more reliable, the star counts, photographic counts, or Shapley's clusters? And furthermore, what is the distance to the Andromeda Galaxy? And what's funny is there was a nova event that happened in the Andromeda Nebula, which was called Messier Object 31, and it was still called the Andromeda Nebula. And it was called the largest spiral nebula at the time. And so we look at this thing and we say, well, how far away is it? And there was a nova that was discovered, and that nova had some regular outbursts. And I thought, well, okay, let's see if we can calibrate that and find the distance to that. And finally, what is the motion of the spiral nebulae themselves? Is there a rotation that they're actually rotating? And what are their radial velocities? And which is the more important? Here's what Shapley said. Shapley said that the galaxy is about 300,000 light years across, and there was a nova in 1885 that gave a distance because of a luminosity of only 10,000 parsecs. That's smaller than his idea for the size of the galaxy, and so therefore M31 had to be internal. And interestingly enough, Adrian van Manen discovered a proper rotation for Messier Object 101. That was his observation of the rotation of a galaxy. So he thought it had a very large rotation that was actually discoverable. And Shapley used that and said, well, if M101 were really distant, and for us to actually be able to see that rotation speed, then it would have to be rotating faster than the speed of light. So combining together conventional physics about the formation of stars, or at least of how stars might form and how planets might form, and all sorts of other things, Shapley had some pretty decent arguments for the concept of the nebular hypothesis for the spiral nebulae, and thus the tiny Milky Way with respect to the universe. Curtis, however, said, well, a typical nova in Andromeda gave it a distance of much further. So that's really odd. So the single nova that Shapley was talking about made it close. But if a typical nova was out there, it's very far, and so therefore the distance is about 10 kiloparsecs. And that gave it roughly a size of Kapteyn's Milky Way at that distance, and so therefore it's an external object and really far. He also argued extensively that the Earl of Ross's original dark obscuring bands that he saw with the Leviathan, and we're seeing with subsequent telescopes for a long time, are just simply edge-on spirals, and they're just like you would see in the Milky Way. So the characteristic of the edge-on spirals would be take a spiral galaxy, a spiral nebula, and look at it edge-on, and you've got this disky dark structure, and you've got a line through it, which is exactly the Milky Way. So they must be similar objects. And finally, he said, well, the spiral nebulae have really large radial velocities, so they should be able to escape the Milky Way. Problem is there's lots of shoulds in his arguments. Now, there was no winner to the Great Debate, and that's the problem. And it was basically get everybody in a room and air the grievances. So there was airing of grievances in this debate. Shapley had the more compelling observational evidence because he felt like he did, but the evidence was flawed. And Curtis ended up being right, but his observational evidence was weak, because he said, just look at this thing, it's edge-on, and if it's edge-on, it could be that. Well, lots of things can be edge-on. So the observational evidence that Curtis chose did not exclude other ideas. There were a lot of things with the debate, and so it was still inconclusive, but the big problem was nobody had a good distance to the Andromeda Nebula, and no one could reproduce Feynman's proper motion of M101. Nobody could. Hint, because it's so far away, nobody ever would. So it was a mistaken observation, so darn him. And didn't take long. 3 years later, Edwin Powell Hubble ends that debate. He used the 100-inch telescope in Mount Wilson in California and looked for Cepheid variables in the Andromeda Nebula. He used Shapley's version of Leavitt's period luminosity relation for the Cepheid variables, and he got a really great distance to the M31 of 300 kiloparsecs. And that's far bigger than the Milky Way, according to Shapley. So no matter what, M31 is outside the Milky Way. He kept at it, and by 1925 he got better data, and he got even more Cepheid variables in Andromeda. And he found that even a greater distance of 1,000 kiloparsecs. So he thought it was an incredibly distant object, and so therefore it must be much more distant, it's outside our galaxy, and it must be at least as big as the Milky Way. And he ended the distance debate and ushered in a new era. Because it's starting at this time, we now knew that the universe was extraordinarily large and not just the purview of the galaxies. And in fact, this is what Einstein even said when he thought about general relativity. His original work before that, 20 years prior, assumed that the stars were the universe. And now Hubble comes along and says, well, the universe is really much bigger. So the universe grew in size radically. Nobody knew how big it really was. But in 1925, the concept of how big the cosmos was changed forever. And so here's what he looked for. Here are some of Hubble's actual data. It has a particular appearance to the Cepheid variables in M33 and M31. And here are the ones that he marked down and looked for specific Cepheid variables, and showed that both these objects could be too far away. And here's one of his photographic plates where he actually marked variable stars. He actually figured out and found that there was a variable star. So here's a really interesting thing. Here's a 1923 photograph that he took from the 100-inch telescope on Mount Wilson. And here's another set of photographs that he took in 1926, or at least they were released in Astrophysical Journal, where he noted novas and Cepheid variables all throughout M33, the triangulum galaxy. And this led him to understand that these things were incredibly distant. In fact, M100, which is another spiral galaxy, also has Cepheid variables in it, and we can see this Hubble Space Telescope observation with the Wide Field Planetary Camera too. And finally, Dave Soderblom of the Space Telescope Science Institute in 2011 published in 2011 his observations of Hubble's exact field. And so he wanted to actually take an image of what Hubble looked at. And so his Hubble Space Telescope images confirmed using the Wide Field Planetary Camera 3 and the UV integrated spectrograph to discover the variability of it using the Hubble Space Telescope. So literally, Hubble looks at Hubble's original data, and showed the variability of this star that was in Hubble's first diagram, in his first discovery image from 1923. And so the light curve of the Cepheid variable star can be seen here, and this is all out of the Hubble site archive, May of 2011. So we can see here's the little stars that show the 4 observations that they got with Hubble time, and if that is the light curve from Hubble's data, then we can see that the brightness closely matches the expected light curve, which is fantastic. Other galaxies have them, such as M100, and there's an up-close picture of a Cepheid variable in M100, and other other Cepheids exist in other spiral galaxies, such as NGC 3021. This is another view by Adam Rees, also utilizing it at Johns Hopkins, hunting for Cepheid variables in stars. And his goal was to actually get Cepheid variable distances because he was looking for supernovae in 1995. So you can see that he's looking for another form of standard candle, which is the supernova 1995 AI, which is what he's looking for, actually. And that was his goal once he found that supernova. He looked distinctly for Cepheid variables inside of that galaxy in order to get conclusive distances to that galaxy so he could calibrate the distance using that supernova's light. We'll see that becomes really important later. So in 1936, Edwin Hubble published his book called The Realm of the Nebulae, and it is one of the most important picture books that has been published in astronomy. It showed really a fantastic set of images. He discovered that the spiral nebulae were actually, now we call them spiral galaxies, and the Milky Way is now just the galaxy, and all the spiral nebulae are now called spiral galaxies. And they're just like the Milky Way. Their sizes are about tens of kiloparsecs across. Their distances are megaparsecs, or millions of parsecs. And basically, he's asked some of the fundamental questions, and they still are, they're still relevant questions today. So if you go and find that picture, it's an amazing thing. I'm sure it's like a few $1,000s on Amazon if you want to get a used copy. In fact, I doubt you can actually buy a copy, and most of them are in research libraries. Now our current view of the Milky Way is that the sun is about 24,000 or 30,000 light years from the center, and the center is in the direction of the Sagittarius. The disk is about 30,000 or 100,000 light years across, or 30,000 parsecs across, and it's about 1,000 parsecs thick, or about 3,000 light years thick, where the sun is. And the middle left-hand image comes from the 2-micron all-sky survey, and the other image is an illustration that's been done by the Spitzer Space Telescope group that shows where the sun is and the rough distribution of the galaxy. So this is what we meant by Earl of Ross's idea of what the Milky Way may look like from a distance. And this is a really good detailed image of NGC 891, which shows a dark band of dust going across the center, cutting across it. And so if we got millions of light years away from the Milky Way and looked at it edge on, this is probably what we would see. Something very similar. Dusty band, some sort of bright bulge in the middle, and a halo of stars around it, some bright pinkish glows from star-forming regions, and bright stars dotting its lanes, which would be O and B type stars. And so we would call NGC 891 as a Milky Way analog, or something that we might think of as the Milky Way. And so we would say that's the galactic center. And so if this is what the Milky Way would be, the sun would be about 8,000 parsecs from the center. The galactic bulge would be that bulge that we call the center, and the disk would be the galactic disk. So this is what the Milky Way might look like from a distance if we were able to get millions of light years away. So Milky Way, Andromeda are spiral galaxies, and that gives us our rough idea. Where do the globular clusters fit in? Well, the globular clusters make up a halo or spheroid of stars and gas, mostly stars, that make up the halo around the center of the Milky Way. And so Shapley's globular clusters are truly centered on the center of the Milky Way, and that's what we know today. And that's our rough picture for it. O and B type stars are in the disk. Globular clusters are above and below the disk. There's a huge bulge of stars, a galactic bulge, and the gas and dust is primarily confined to the disk of the Milky Way. We saw pink emission nebulae that are like Orion star-forming regions, or Trifid nebula star-forming regions that are in the disk. And so the gas and dust is in the disk, the hot stars are in the disk, star formation is in the disk, and the globular clusters are above and below. And this is kind of our image for the Milky Way that we have today. And this comes from the Space Telescope Science Institute, as well as NASA JPL. This is Hertz from SSC, and this is part of the GLIMPSE team from Caltech. If the sun is going around at roughly 200 kilometers per second around the orbit, it will take over 226 million years for the solar system to orbit the center of the Milky Way. If we are at 6 o'clock now on this location here. Then the dinosaurs died out. If we're thinking about it as being a clockwise rotation, then if we're at 6 o'clock, the dinosaurs died out about 60 million years ago, and if it takes about 226 million years to go around once, then the dinosaurs died out roughly between 2 o'clock and 3 o'clock on this diagram, which is really interesting. The age of the Earth is only about 4.5 billion years. So 4.5 billion divided by 226 million, so 4 times each one. So you got 4 to make a billion. So 4 orbits times 4 is 16, 17, 18 orbits. So the Sun and the solar system has only orbited the center of the Milky Way 18 times. So I guess it could get drafted by the US Selective Service. But it still isn't old enough to drink. That's another 3 more orbits. That's in 700 million years. Okay, that's what we call the cosmic distance ladder. And we start from the Earth, where we do radar ranging to get to the various planets. And that's the astronomical unit. We use the stellar parallax to get us out to the stars. Once we calibrate the stellar parallax with spectroscopic parallax, we then get distant star clusters. We use distant star clusters to get us variable stars. Variable stars get us out to distant galaxies, and that's how we know the distance to the Andromeda galaxy and beyond. And so this is our picture of the local group of galaxies. The Milky Way is one galaxy. The Andromeda galaxy, M31, is another one. They're separated by an enormous, vast gulf of distance of over 3 million light years. And that gulf is enormous. The size of the Milky Way is 100,000 light years across, and so is the Andromeda. The Triangulum galaxy is there. But in between are tiny little dwarf galaxies and vast emptiness of space. And that's what we call the local group of galaxies, this group of galaxies. And that's how we know how far the Andromeda is, by looking for Cepheid variables. And that was the great debate of 1920. The result of it is that the universe became really quite large.